Yes, Sandeep, I can hear you. Debarga was trying.
Yeah, is it okay now? Can you say something? I mean, just to confirm that I'm able to hear you, right?
Sandeep, can you hear us?
Yes, now I can hear you. Thank you.
Okay.
Yeah, thank you.
Hello.
Yeah, so let me share my screen, if you don't mind.
Yeah, please go ahead.
Yeah. Can you see?
You have not yet shared your screen, no?
Oh, I thought the screen was shared. Wait.
No, it is not.
Okay. What about now?
No. Are you a host, co-host? You have the rights to share, right?
Yeah, it doesn't allow me to share a particular window though. So it does say that the participants can see my application. I don't know what that means.
Okay, let me talk to Media Center. Maybe they need to give you permissions to share.
Sandeep, you would be able to do share screen now.
Okay, so now I'm not able to go back to the. Hello? Yeah, but I shared the screen and it's somehow not allowing me to.
Can you try once again?
Okay. Yeah, let me. Yeah, it's not giving me options to share the screen somehow. No, I'm not able to see that. You see, let me. What you can see something? This screen. What is the screen that you see right now? No, but it's. I want to figure out how to share the screen, right? No, it is not like, somehow this Zoom is not showing me the share screen. So let me log out and re-log in then, because, somehow it's kind yeah. I opened my PDF. Of course, I opened the PDF, but see, the thing is, I cannot see Zoom screen at all. Okay. So in that page, all I am seeing is myself. Yeah. Hello? 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 Hi. Yeah, that's what I'm trying to do. That's exactly what I'm trying to do. No, I logged out. I don't know why it is not showing up as my logging out. No, but that's a glitch in the application. I actually logged out. So let me just. Uh, Hello? I'm just logging onto the next computer. Yeah. I'll do it. Yeah.
Okay, now can you hear me? Okay. Okay. It's causing me. Hello? Hello?
Sandeep, we can hear you.
You can hear me?
Yes, yes.
Oh, okay, good. So let me continue with this then. Though I can only very feebly hear you. You know, it's the volume is really low. So anyway, let me try with this. So if you have questions, maybe please use the chat because you know I'm unable to. So let G be a finite group and let Z of G stand for the Bernstein center of G. Okay, so I should explain what is Bernstein center for a finite group. So for a finite group G by Bernstein center, I just mean it's a ring of class functions. Okay, so those functions are from G to C, which are invariant under conjugation. So let me write the irreducible representations of G, Ir of G, or equivalently omega of G as pi 1 V1 up to pi n Vn. So these are the irreducible representations of G. So recall from the representation theory of finite groups that we have the group algebra of G, which I am writing by C of G. And what do I mean by C of G? It is the set of all complex valued functions from G to C. Okay. The group algebra is isomorphic to product of the matrix algebras over the endomorphism ring of G. In other words, given element f in the group algebra, I can map it to pi 1 of f up to pi n of f, where pi of f denotes the action of f on the space of pi, namely integral over G, f of G, pi of G dg. Okay, so the group algebra is equal to the product of a bunch of endomorphism algebras, and inside that, what happens to the ring of class functions? The class functions map to the product of endomorphisms of algebra, but this time the difference is that at the ith position, instead of mapping into the C endomorphisms of Vi, you are mapping into the G endomorphisms of Vi. Okay, so what does that mean? Since by Schur's lemma, the G endomorphisms of Vi are just the scalars, so you have the product from I equals 1 to n of just the complex numbers. Okay, so in other words, the ring of class functions can be thought of as the ring of maps from omega of G to C, where omega of G is the same as Ir of G. Okay, so I'll refer to omega of G as the Bernstein variety of G. Okay, so so I should say that the group algebra is a ring under convolution. So on C of G, G2, the ring operation is convolution and not pointwise multiplication, although it was a ring of functions. But on the other hand, when you think of it as functions on omega of G, the ring operation is multiplication, the usual pointwise multiplication. So let me start it as a presentation. Yeah, so for Z belonging to C of GG, the following are equivalent. First one, Z belongs to C of GG. Secondly, for each representation pi comma V, pi of Z actually belongs to a G endomorphism of V and not just a C endomorphism of V. And the third equivalent condition is that if pi comma V is irreducible, then pi of Z is given by multiplication by a scalar, namely Z of pi. Okay. So is this okay? Okay, so I can't even hear a response.
Yes, Sandeep, we can
okay,
hear.
Okay. So let me go ahead. Actually, I can only hear you very feebly. So I have just copied down the 3 equivalent definitions of Z of G from the previous slide over here. Okay, so let me restate the second condition over there. One can restate the second condition as saying that sending a representation pi v to the action of pi of z is actually an endomorphism of the identity functor on the category of complex representations of G. Okay, what does this mean? If you apply the identity functor to an object, you get the same object. So to say an endomorphism of the identity functor is to say that for each object, you are looking at an endomorphism of the object in a manner that is compatible with the morphisms in the category. Okay, so endomorphisms of the identity functor are some very simple-minded thing. You are just constructing a ring which acts on each object of the category in a manner that is compatible with the morphism. Okay, so to say that pi of z belongs to ng of v rather than just nc of v is to say that sending pi to pi of z is an endomorphism of the identity functor on the category of complex representations. In other words, the ring of class functions acts on the category of complex representations of G. Okay, so the equivalence between 1 and 3 can be rewritten as follows. As in the previous slide, the ring of class functions under convolution can be written as a product of copies of complex numbers corresponding to irreducible representations of G. And this can be written as an isomorphism from the convolution algebra of class functions to the ring of regular functions on the Bernstein variety omega of G, sending a class function Z to the function that sends an irreducible representation pi to the scalar Z tilde of pi with which pi of Z acts on the space of pi. Okay, so I'm spending some time to discuss all this because in the case of periodic groups, everything is going to be a very perfect analogy. So we need to keep in mind the notation regarding the finite groups very clearly. Okay, so now let me move on to the next page. Okay, so now we are going to give a double role to the ring of class functions. On one hand, we'll think of it as a ring under convolution. On the other hand, I'll also think of C of G upper G as it is the span of irreducible characters of G. Okay, so it's the sum of C times the character theta pi of the representation pi. And I'll think of this space as D temp of G. Okay, so don't worry about temp now. Later we'll be interested in what are called tempered representations. That's why I'm writing it. So instead of thinking of class functions as a ring, I'm thinking of the class functions as operating by its left multiplication or left convolution action on D temp of G. Okay, so then up to scalars, the set irreducible characters theta pi can be simply recovered as the eigenspaces for the action of Z of G on D temp of G. Okay, so any questions so far? Okay, let me go ahead. So I can see actually Supriya on the screen. So I hope Supriya will let me know if someone is asking a question. So now let us go to a periodic group. Okay, so how do we generalize all of these to a connected reductive group G over a periodic F group, periodic field F, which is a finite extension of QP? So throughout this talk, I'll assume that my group G is actually quasi-split. So the obvious generalization of the group algebra to the periodic setting is just CC infinity of G of F, namely the set of compactly supported locally constant functions on G of F, which are a algebra under convolution. However, we should not generalize class functions as the set of G of F invariant functions on CC infinity of G of F, because there aren't too many such functions, because there are too many elements which are not close to the identity but become arbitrarily close to the identity on conjugation. So instead, we need to enlarge CC infinity of G of F into the larger space of what are called distributions, which is the C linear dual of CC infinity of G of F. Okay, so home C of CC infinity of G of F comma C is a very large space, because given any reasonable functions on G, you can integrate it against a CC infinity of an element of CC infinity of G of F and think of it as a distribution. And inside that, you can look at those which are invariant under conjugation. Okay, so these are the conjugation invariant distributions, or the so-called invariant distributions. So this is the space of interest under consideration. So there are two important examples of invariant distributions. The first are the so-called orbital integrals. Namely, if gamma is an element of G of f, then I can send an element f in CC infinity of G of f to the integral of f over the conjugacy class of gamma. Okay, so integral f of G inverse gamma G dg. So this generalizes one of the basis elements for the usual basis for class function for a finite group, namely the characteristic function of conjugacy classes. Okay, so orbital integrals generalize that. And the second basis for class functions is given by characters, and they can be also generalized to the notion of periodic groups if you move on to distributions. Namely, given an irreducible smooth representation of G, you can consider its associated character theta pi. Theta pi is that distribution on G which sends an element of CC infinity of G of f to the trace of pi of f, where pi of f is the action of f on the space of pi, namely integral f of G pi of G dg. Okay. So for some reason, we don't want to look at the span of theta pi over all the irreducible smooth pi. Instead, we are only going to look at the span of pi over all the tempered pi. Okay. So in this talk, you will not need the precise definition of the word tempered. So please take that as a black box. Okay. So this is the notion of distribution. Again, this is going to be quite important in what follows. Any questions yet? Okay, so let me proceed. So now let me define the Bernstein center. So although invariant distributions are an important notion, when you use this as a generalization of class functions, you are missing out on a very important notion from the finite group situation. Namely, you could convolve class functions and form a ring. That was very important. Here, that is not possible because convolution of distributions is not well defined. Okay. There are three equivalent definitions for Z of G. Bernstein, however, realized that one could tweak the definition of an invariant distribution, one could strengthen it and get a ring under convolution. So I'm going to discuss the three equivalent definitions, which are going to be parallel to the three definitions that I gave in the finite group case. The first definition was the definition as class functions under convolution. So for this, you cannot look at all the invariant distributions because their convolution is not well defined. So you should look at specific invariant distributions. Namely, you can convolve any distribution with a CC infinity function. However, the result of such a convolution is a C infinity function, not a CC infinity function. So you look at those distributions whose convolution with CC infinity again belongs to CC infinity. Okay. So it is reasonable to think that if you can repeat, since you can repeat this sort of a process inductively, they should form a ring. Okay. So such distributions are called essentially compact distributions. So these generalize the realization of Z of G as the ring of class functions under convolution. The second description of Z of G was the endomorphism of identity functor on the category of representations. So here you should look at the category of what are called smooth representations. In other words, here every element of Z of G is not a function. It is a distribution. So you cannot talk of integral pi of G, Z of G dg on the nose, but still, one can make sure that pi of Z makes sense. One can somehow make sense of pi of Z, and then observe that each pi of Z is actually an endomorphism of the representation pi. It's a G endomorphism of pi and not just a C linear endomorphism. So you can actually realize Z of G as the ring of endomorphisms of the identity functor on this category. The third realization of the ring of class functions, namely as the set of all regular functions on the Bernstein variety, also can be generalized, except that here you have to take care of two different points. First of all, you don't want to look at all the irreducible smooth representations, because if you take a parabolically induced representation on all the irreducible quotients of the subquotients of the parabolically induced representation, it so turns out that an element of the Bernstein center acts by the same scalar. So instead of looking at all the representations pi of G, what you look at is the set of all pairs m comma pi, where m is a Levy subgroup of G and pi is a supercuspidal representation of m of f. Okay. So from such pairs m comma pi, it so turns out that you can form a variety omega of G. Okay. So, just for those who are familiar with Tate's thesis, just like in Tate's thesis, the set of characters of M can be viewed as a disjoint union of tori, complex tori. And one can use that idea to collect together the pairs M comma pi and form them into a variety omega of G. It will be of infinite type. It will be an infinite union of finite quotients of tori. So that variety is called the Bernstein variety. And one can also realize the Bernstein center as the ring of not arbitrary functions on omega of G, but the ring of regular functions on the variety omega of G. Okay. So these are the three realizations. Okay. So how do you go between these three realizations? To go from realization 1 to realization 2, notice that what realization 1 does is to define an action of the Bernstein center by convolution on the regular representation CC infinity of G of f. Once you define it on the regular representation, you can define it on all other representations because regular representation is the mother of all representations. To go from 2 to 3, you just apply Schur's lemma. Once you have a G linear action on every representation, by Schur's lemma on irreducible representation, it has to act by a scalar, Z tilde of pi. Okay, and then one realizes it as a regular function on actually the Bernstein variety because it depends only on the cuspidal support. Okay, so notice that Z of G acts on CC infinity of G of f by convolution. So just from that fact, Z of G acts on a wide variety of things associated to G, and in particular, it acts on invariant distributions on G of f, and on the character theta pi of any representation pi, it acts as multiplication by the scalar Z tilde of pi. Okay. However, this time there is one difference with the finite group case. The eigenspaces of Z of G on D temp of G, by which I mean those distributions on G which are finite linear combinations of tempered characters of G. These eigenspaces are not just C times theta pi, because if pi 1 and pi 2 are irreducible subquotients of the same parabolically induced representation, then Z of G acts by the same character, same eigen character on both of those. Okay. So any questions yet? Shall I proceed? Okay, let me go ahead. So I don't see any chat either. So I'll just assume that it's all okay. So now so the title was about stable Bernstein centers, and therefore sorry, there was a missed phone call. Was there a question or something? Sorry? So Supriya, can you hear us?
Sandeep, I can hear you clearly.
Okay, so I'm now hearing something vaguely from your side, actually. Yeah. Yeah. Okay. Yeah. I'll do that. Yeah. Thank you. Okay, so let me recall. So to define stability, let me recall the basic statement of the local Langlands correspondence. So remember that Langlands correspondence basically says that to every modular form, you can associate a Galois representation. Here we are working locally over a local field. the local analog of a modular form is an element of Ir of G. So an irreducible smooth representation of G of F. And what is the local analog of a Galois representation? If your G was GLN, your Galois representation would be a homomorphism from the Galois group of F into GLN of C taken up to conjugacy by GLN of C. Okay, so here instead of GLN, instead of the Galois group, one has to look at the Weyl group cross SL2C, that is called the Weyl-Deligne group, and instead of conjugacy by GLN of C, one has to take conjugations under what is known as the Langlands dual group of G. Okay, so the local Langlands correspondence posits the existence of a finite to one surjection. Okay, actually one did not need G split here. Okay, so as I have written over here, the statement is quite meaningless because both Ir of G and the right hand side both are countably infinite sets. So obviously they are going to be in surjection, in bijection, let alone finite to one surjection. But the point is that to make it natural is part of the question. Namely, one has to come up with some natural conditions and then say that there is a unique finite to one surjection subject to those conditions. Okay, so it so turns out that once your group is more general than GLN, the fibers of this surjection are not singleton, but they are actually finite sets. These finite sets are what are called L packets. They are still conjectural because local Langlands correspondence itself is conjectural. And philosophically, the following is the reason why L packets are not singleton. Namely, if you have an element gamma in G of F, then you can consider the conjugacy class of gamma, namely the set of all G of F conjugates of gamma, which is what I have written on the right hand side here. On the other hand, you can look at all the G of F bar conjugates on gamma and intersect with G of F. That is roughly speaking what is called the stable conjugacy class of gamma. So for GLN, one knows that two matrices are conjugate if and only if they are conjugate over the algebraic closure. But this equality is not true for a general reductive group. The difference is somehow finite in nature. And this is why philosophically L packets are expected to be singleton. Okay. So in other words, let me repeat, the phenomenon of L packets being singleton reflects the assertion that for a general reductive group, stable conjugacy is strictly coarser than conjugacy. Okay, so this might look very weird and goofy. So let me actually repeat this in yet another way. Again, let us go back to a finite group. Okay, what is representation theory of a finite group? Basically, representation theory of finite group is invariant harmonic analysis on the group. Namely, you are studying functions on the group which are invariant under conjugation. Okay, but you see the right hand side that I had written over here does not okay, so let's not look at the right hand side, but the point is that it so turns out that the phenomenon of L packets does not have anything to do with G of F conjugation on G of F, but rather it has something to do with G of F bar conjugation on G of F. Okay, so namely, if the usual representation theory of G of F studies G of F conjugacy on G of F, the phenomenon of L packets involves G of F bar conjugacy on G of F. Okay, so somehow the fact that characters are a basis for class functions should be changed to a statement about L packets, or like, a coarser set of objects giving you a basis for not class functions, but functions which are invariant under stable conjugacy rather than the usual conjugacy. Okay. But the definition of a stable distribution is more non-trivial than the definition of an invariant distribution, because you can, G of F acts by conjugation on G of F, but G of F bar does not act by conjugation on G of F, because if you G of F bar conjugate G of F, you go outside G of F. So to define a stable distribution, one has to rephrase the usual definition of an invariant distribution and then generalize that definition to the definition of a stable distribution. Okay, so one has to use the following fact: a distribution from CC infinity of G of F to C is invariant if and only if it vanishes on all functions whose orbital integrals are 0. Okay, so this might look a bit mysterious. So let me explain this by analogy with finite group terms. For finite groups, a class function is 0 if and only if it is 0 on each conjugacy class. Okay. In other words, characteristic functions of class conjugacy classes are a basis for the space of invariant distributions on a finite group. Here, this is saying that roughly the same is true for invariant distributions with respect to orbital integrals. Namely, the span of orbital integrals is not quite a basis for the space of invariant distributions, but in some sense, the space of invariant distributions is the closure of the space of orbital integrals. Namely, if a function is 0 on every orbital integral, it should be 0 on every invariant distribution. Okay, so this is the definition of an invariant distribution. Okay, so now the notion of an orbital integral can be generalized to a stable orbital integral. Namely, instead of integrating a function over each conjugacy class, you can integrate a function over each stable conjugacy class. Namely, you look at the conjugacy class of gamma with respect to g of f bar and intersect with g of f. Okay, so that defines you for the notion of a stable orbital integral, and one says that a distribution is stably invariant or stable if it vanishes on all functions whose stable orbital integrals are 0. Okay, so this allows you to generalize the notion of a characteristic function of a conjugacy class to a stable conjugacy class, and then to make sense of that at the level of distributions. So now the point is that if you can somehow generalize that to the cadre of representation theory as opposed to just distributions, then you can define L packets. That's the philosophy of the theory of stability. In other words, the expectation is that tempered representations of G of f can be partitioned as a union of finite sets called tempered L packets with the following property. The first property is that for every L packet pi, there is some linear combination of characters of that L packet, which is actually not simply a tempered character, but which is actually stable. Okay. So in other words, for a distribution, being stable is actually a stronger condition than being simply invariant. So the point is that the character of an individual representation may not be stable, but if you take a single L packet, there is some linear combination of the characters of its elements which is actually stable. Okay, that's the first condition. Second condition is that any stable tempered character, that is, any linear combination of tempered characters which is stable, is uniquely a linear combination of the linear combinations that I assigned in the first associated to the tempered L packets. Okay, so in other words, just like characters gave you a basis for the space of class functions, stable characters, namely this theta capital pi, should give you a basis for the space of stable tempered characters. Okay, so in other words, there should be some way to generalize the notion of the notion of stability applied to tempered characters decomposes very nicely into packets of distributions. That's the philosophy of stable tempered characters. Okay, so now here there is one advantage as opposed to the statement of the local Langlands correspondence. The statement of the local Langlands correspondence was vague because there could be any number of bijections. One has to make precise what it means to be natural. But here, if you look at the definition that I have just written down over here, it is easy to see that if you can partition tempered representations into L packets in the manner that I have written over here, such a partition is necessarily unique. The only problem is that it is not clear that such a partition actually exists. Okay, so now I have described how the theory of invariant distributions manifests at the level of stability. But this is not our prime interest over here. Our prime interest was in the Bernstein Center. Remember that Bernstein modified the notion of an invariant distribution to form the notion of a Bernstein Center. So the question here is what should deserve to be called the stable Bernstein center of a reductive group. Okay. So the point is that conjecturally we should have some subring of the Bernstein center called the stable Bernstein center. Okay. And remember, the Bernstein center acted on every irreducible, every invariant distribution on G. In particular, it acts on the space of tempered characters of G. And the conjecturally, what we would like is that if you restrict that action to the stable Bernstein center, then something nice happens. Namely, the common eigenspaces for the action of the stable Bernstein center on the space of stable tempered characters or on the space of tempered characters should be simply given in the should be indexed by the tempered L packets. Namely, given any tempered L packet capital pi, the sum of the characters theta pi as little pi varies over capital pi should be a common eigenspace for the stable Bernstein center. And secondly, these should precisely be the common eigenspaces for the stable Bernstein center. Okay. Since this is an important statement, let me rephrase it. The condition is as follows. If you have two tempered representations pi 1 and pi 2 and pi 2 belonging to the same tempered L packet should be the same as saying that every element of the stable Bernstein center should act by the same character on both pi 1 and pi 2. Okay. So in other words, if you can define and prove enough properties about the stable Bernstein center, you will be able to completely know everything about the partition of tempered representations into L packets. Okay, why tempered? This should be compared with the following fact. For real groups, the infinitesimal character determines the discrete series L packet. Okay. So I said that conjecturally we should have a notion of stable Bernstein center. And now what are the candidates to be that deserve to be called stable Bernstein center if you are given a general periodic reductive group? Okay. So remember, every element of the Bernstein center has a double role. One, you can think of it as a distribution from CC infinity of G of F to C. Secondly, you can also make it act on CC infinity of G of F. And the point is that there is a very simple relation between these two perspectives. Namely, Z as a distribution can be recovered from the action of Z basically by to evaluate Z as a distribution on F, simply make Z act on F and evaluate at 1. Okay, so that is all that is there to it. Okay, now here are the two candidates for the stable Bernstein center. One, you look at those Z element of Z of G, the Bernstein center, that as a distribution are stable. Okay, so that forms some vector subspace of the Bernstein center. You call it Z1 of G. The second candidate is as follows. You look at those Z element of Z of G such that if you are given a stable distribution D, Z star D should be stable. Okay, it is easy to see that such Z form a subring of the Bernstein center. You call it Z2 of G. Okay, so it so turns out that both Z1 of G and Z2 of G are candidates for ZST of G. Okay, so let me mention an equivalent characterization for Z2 of G. So recall that how did I define a stable distribution? I defined a stable distribution as that distribution which vanishes on all functions whose stable orbital integrals vanish. Okay, so an equivalent characterization is that instead of requiring Z to preserve stable distributions, you can also require Z to preserve those functions whose stable orbital integrals vanish. These are called the unstable functions. Okay, so you have two different candidates which are defined in complete generality and which are both candidates for being called the stable Bernstein center. Okay, the catch is that we need to prove properties about these Z1 of G and Z2 of G and then get enough information about L packets. Okay, so that hasn't been done in generality. And it is easy to prove that Z2 of G is contained in Z1 of G. It's an easy Shalaika-Germs argument, but due to lack of time, let me not discuss it. Okay, so you have two different candidates. One of them is obviously contained in the other. the ring is contained in the subspace. Okay, Z2 of G is a ring. It is contained in Z1 of G, which is a subspace. And the stable center conjecture, one form of it says that Z2 of G and Z1 of G are one and the same. Okay. Another form of the stable conjecture center conjecture says is that Z1 of G is actually a ring. Are these two formulations equivalent? I don't know. But these two are both forms of the stable center conjecture. Okay. Who is this conjecture due to? This conjecture is due to many people. It is due, you can think of it as due to Haynes. You can think of it as due to Bezrukov, Karzan, Warshawski. You can think of it as due to Scholz and Shin. Okay. Now, the first statement, first proposition that I would like to discuss for today is that if there is a good way to define discrete series packet on each Levy subgroup of G, then one can actually prove the conjecture. Okay. Namely, so I have left some space between the main assertion of the proposition at the end and the assumptions in the proposition. That is to actually fill in details for what I mean by this assumption. Okay. So if there is a good way to define discrete series L packets, then the conjecture is true. That is what the proposition is saying. And Arthur has defined discrete series L packets in a good way. And therefore, one knows that the conjecture is true for symplectic groups and odd special orthogonal groups. Okay. So in fact, it's actually true for even special orthogonal groups too, except that one needs to do a little bit involving an outer automorphism. So let me not discuss that. Again, because I don't have time, let me not make sense of what it means to say that we have discrete series L packets. It's exactly the same as what I wrote for tempered L packets earlier. Just like I said, we should have a conjectural definition of tempered L packets. One should have something very similar, except that the word tempered should be replaced by discrete series. And we should have it not just for G, but we should have it for every Levy subgroup of G. Okay. So that is the proposition. And I'm not going to discuss the proof, but the proof actually goes through showing that each of these two conditions is equivalent to a third condition. The third condition is to say that the action of Z is actually constant on each tempered L packet. Namely, if you can define discrete series L packets on each Levy subgroup of G, then parabolic induction allows you to define a tempered L packet on G, tempered L packets on G, and the condition is that the action of Z should be the same on constants of each tempered L packet. Okay, then one can actually show the conjecture. Okay, so all I'll say about the proof is that it follows Shahidi's argument from his 1990 annals that the Plancherel measure is constant on tempered L packets. Okay, let me not say more about the proof because I don't have enough time. I anyway started late. But one thing that I'll say is that the proof is not hard at all. One is basically following Shahidi, but it makes use of a deep result of Arthur, namely to show that all the stable orbital integrals of a function vanish. It is enough to show that all the stable tempered characters vanish on that function. Okay. So let me not make this extra comment. The extra comment says that sometimes even if you do not have discrete series L packets on all the Levy subgroups, if you have a candidate for a single discrete series L packet which satisfies some reasonable property, then you can make some limited statement. Okay, so let me not discuss it. Okay, so now let me discuss the relation of the stable Bernstein center with what is known as the variety of infinitesimal characters of G. Okay, so for that I need to define what is known as an infinitesimal character for a reductive group G. So remember a bit earlier. Okay, so I have 10 minutes extra. I can have 10 minutes extra. I guess that means I have 15 minutes in total. Thank you. So let me define what is known as an infinitesimal character. So a few slides ago, I discussed what is called a Langlands parameter. A Langlands parameter for G was a homomorphism from WF cross SL2C to LG taken up to G hat conjugacy. from the notion of a Lagrange parameter, if you remove the SL2C, what you get is an infinitesimal character. Okay. So if you look at the set of all infinitesimal character, there is a way to organize them to form a variety that is called the variety of infinitesimal characters, and I'll denote it by omega of Lg. Why is this related to the Bernstein center at all? The reason is that a Lagrange parameter WF cross SL2C to Lg is believed to parameterize a supercuspidal L packet if and only if it is trivial on SL2C. So infinitesimal characters should correspond to supercuspidal packets on levies. That's how it's related to the notion of a Bernstein center. So let me describe whatever I just said in a little bit more greater detail. So assume the local Lagrange correspondence. So in other words, for every irreducible representation of G, we have its associated Lagrange parameter phi pi, which is a homomorphism from WF cross SL2C into Lg taken up to G hat conjugacy. Okay, so that is phi pi is what is called the Lagrange parameter of G. From that, you can form its infinitesimal character in the following fashion. Namely, somehow one has to get rid of the SL2C here. What one does is, one chooses an embedding from WF into WF cross SL2C. Okay, but this is not the obvious embedding. Instead, one has to take the embedding where W in WF maps to W comma the diagonal matrix in SL2C with eigenvalues norm W to the half and norm W to the minus half. Okay, so if you compose that, you get, starting from the infinitesimal character of pi, you get starting from the Lagrange parameter of pi, you get what is called the infinitesimal character of pi, namely lambda phi pi. Okay, so in other words, to every pi, you can associate an infinitesimal character in omega of G. Okay, so now let me discuss the connection between omega of Lg and the Bernstein center. So how do you map the coordinate ring of the variety omega of Lg into the Bernstein center? So recall that the Bernstein center itself is the coordinate ring of regular functions on omega of G, which, recall, was the set of all pairs m comma pi, where m was a Levy subgroup and pi was a supercuspidal representation taken up to G of F conjugacy. Okay, so to embed the coordinate ring of omega of Lg into Z of G, it is enough to map the Bernstein variety into omega of Lg. Okay, if you can map at the level of varieties, then take the corresponding map of coordinate rings and you get the map from C of omega of Lg to C of omega of G. Okay, so how do you have this map? This map is defined as follows. Given a cuspidal pair m comma pi, you simply take the infinitesimal character of pi. Okay, so that gives you something valued in Lm, but then you can inject Lm into Lg. So composing, you get an infinitesimal character for G. So you get a map from omega of G into omega of Lg, and at the level of coordinate rings, you can map C of omega of Lg into C of omega of G, which is Z of G. Okay, and Haynes showed that all this works well. Namely, the map omega of G to omega of Lg that I discussed above is actually an algebraic map. So the corresponding map at the level of coordinate rings actually makes sense. Okay, so I guess it is almost 10. I have 10 more minutes as per the text message I received. Okay, so the next result I want to discuss is, okay, so you have mapped the coordinate ring of the Bernstein, of the variety of infinitesimal characters into the Bernstein center. The question is, can you relate it to the stable Bernstein center? Okay, so recall that I assume G to be quasi-split, and the conjecture that Haynes and Scholz and Shin and all these people made is that this image of this embedding should be precisely the stable Bernstein center. Okay, so the next theorem that I want to say is that if you allow yourself to believe everything you want to believe about the local Lagrange correspondence, then the expectation of Haynes and Scholz and Shin and all these people is actually true. Namely, assume various properties. First of all, exactly as I described earlier, we should have discrete series L packets on each Levy subgroup. Secondly, we should have local Lagrange correspondence defined with various properties expected of it satisfied. Then the third condition is that those L packets which consist of entirely supercuspidal representations should behave as expected, namely their Langlands parameters should be precisely those that are trivial on SL2C. And then as of now, I need two more conditions which I don't have time to explain. Okay, I'm trying to remove those conditions. So if you assume various properties about the local Langlands correspondence, the statement is that the expectation is actually true. Okay. So any questions? Okay, so let me go ahead. Okay, so now I want to discuss what is called the Z-transfer conjecture of Thomas Haynes. So I'm writing ZST for the stable Bernstein center. So it should equal Z1 of G or Z2 of G, but we don't know that these two are equal even. Okay. So Z-transfer describes how the stable Bernstein center should correspond to what should behave with respect to what is known as endoscopy. Okay. So let H be what is known as an endoscopic group of G. So what is an endoscopic group of G? H is not a subgroup of G, but rather what is true is that the L group of H embeds into the L group of G and satisfies some additional properties. The main property that you require is that the dual group H hat of G is the connected centralizer of some element in the dual group of G. Okay. So the map is purely at the level of dual groups and not at the level of groups at all. Okay. So notice that once the L group of H embeds into the L group of G, Langlands parameters of H can be composed with the embedding of L group of LH to LG, and they can give you Langlands parameters for G. So because Langlands parameters for H map into Langlands parameters for G, L packets for H should map into L packets for G. Okay. So what the theory of endoscopy does is that, all that I have described so far is conjectural because local Langlands itself is conjectural. And what endoscopy does is, it tries to realize this map as dual to a map of stable conjugacy classes from G to H. Okay. So in other words, so remember I told you that L packets are a representation theoretic version of the stable conjugacy classes. Okay. So if you want to transfer L packets, what you should do is to transfer stable conjugacy classes in the opposite direction. In other words, what you should have, at the level of these topological groups, what you conjecturally need is that you should have a correspondence between elements of CC infinity of G of F and CC infinity of H of F. Namely, there should be a way to transfer functions F in CC infinity of G of F to functions FH in CC infinity of H of F, such that their orbital integral should match in some sense, which reflects some sort of transfer of stable conjugacy classes. So the theory of endoscopy defines a very precise map at this transfer of functions at this level. We say that F and FH have matching orbital integrals if that condition is satisfied. And endoscopy says that there should be a transfer of L packets which is dual to this map from FH to F to FH. Okay. So the statement of Z transfer of conjecture of Haynes takes the following form. It says that there should be some suitable map from ZST of G to ZST of H, such that if I denote it as little z map to little zh, then whenever F and FH have matching orbital integrals, then Z acted on F and ZH acted on FH should also have matching orbital integrals. Okay. So in other words, what Haynes Z transfer conjecture says is that there should be, whenever you have H endoscopic to G, there should be a transfer of the stable Bernstein center from G to H, which works compatibly with transfer of matching of orbital integrals. That is the statement of Haynes Z transfer conjecture. Okay. So now suppose H is endoscopic to G. Haynes says something more about how that map from ZST of G to ZST of H should look like. Okay. So to describe this, recall that I had defined the variety of infinitesimal characters. Namely, you look at all admissible homomorphisms from WF into LG taken up to G hat conjugacy. And recall that because H is endoscopic to G, LH embeds into LG. Therefore, omega of LH embeds into omega of LG. On the other hand, recall also that we had embedded Z of omega, the coordinate ring of omega of LG into Z of G, right? So, because we had realized the coordinate ring of omega of LG as contained inside Z of G, namely we realized it as exactly ZST of G inside Z of G. The moment you have LH sitting inside LG, you should have omega of LH sitting inside omega of LG. Therefore, dually, you should have C of omega of LG mapping to C of omega of LH. Therefore, under pullback, you get a map from ZST of G to ZST of H. Okay. So Haynes proposes that the map ZST of G to ZST of H, the map at the level of stable orbital, stable Bernstein centers, should be exactly pullback under the map at the level of infinitesimal characters. But this is not obvious because Haynes does not prove that the map from omega of LH to omega of LG is actually a map of varieties. He says it should be a map of varieties, but there is something to verify there, and that the pullback map should be the transfer of Bernstein center elements. Okay, Haynes describes this for very special elements of the Bernstein center, and I don't think I have time to discuss this because I'm running out of time. Okay, so let me describe what is a conjectural consequence of this. So there is what is known as the fundamental lemma, which says that specific elements in CC infinity of G and specific element in CC infinity of H should match. So what Haynes conjecture tells us is that if you know that specific elements in G and H match, then more elements in G and H match. There is a matching of orbital integrals between more general elements. Okay. So via the Satake isomorphism, once you know that the fundamental lemma, what Haynes tells us is that his Z transfer conjecture will give endoscopic transfer for more general elements for the spherical Hecke algebra of G of F and H of F. Okay. So in other words, the nature of the Z transfer conjecture of Haynes is in the following fashion. It says that if you know fundamental lemma for unit elements, then it gives you fundamental lemma for the full Hecke algebra. And especially, Manish's colleagues would know that recently Manish and Bertrand Lemaire have a work where they look at the Hecke algebra transfer of Alain Roche. They modify the Hecke algebra transfer at the level of centers and verify that it is compatible with endoscopic transfer. But then they observed some strange phenomena there, namely, to get a transfer of functions, you had to do something like a Weil group averaging. Okay. So if you look at the proof of Manish and Bertrand, you will see that it has two steps. The first step is to prove something like a fundamental lemma that I had written over the above. And the second step is to say that once you know the fundamental lemma for the unit elements, you can get the fundamental lemma for the full Hecke algebra. Thus, what the Z transfer conjecture gives you is it gives you a framework to explain why exactly did Lemaire and Mishra have to do that Weil group averaging. Okay, it gives you a framework to think about that. So briefly, what I do here is that I actually show that the map from omega of LH to omega of LG is algebraic, and then show that if you have local Langlands correspondence plus endoscopic character identities and various compatibilities are there, if you assume a lot of things that you can expect, then the Z transfer conjecture should hold. Okay, and it works for twisted endoscopy, it works for Z extensions, but unlike the work of Manish and Lemaire, I have to make all sorts of assumptions about endoscopic transfer. But on the other hand, it allows you to predict, how more kinds of such, transfers might look like. And I hope to prove in later joint work what similar results for, the Bernstein depth R projector might look like. Okay, so I don't think I'll have time to discuss the idea of the proof because I have already run it's already 10:10. I am out of time, so I think I'll stop there. Okay, so sorry for all this confusion. So somehow
Sandeep, can you hear me?
computers working in different ways. So
Sandeep?
So I apologize for all this. So,
Okay.
hello? Yeah. Yeah. Hi. Sorry. Yeah. You see, the thing is that, when you define the variety of infinitesimal characters, one has to actually look at the dual version of unramified characters. So that goes via what is called the Kortewitz isomorphism. And if you look at the Kortewitz isomorphism, you will see that the unramified characters for the levy of H do not map to the unramified characters for the levy of G. Actually things work in the wrong direction somehow. When you have an endoscopy group, somehow the center of G embeds into the center of H rather than the other way around. Or the center of G hat, is somehow landing inside the center of H hat actually, rather. You see, the thing is H hat sits inside G hat, and the condition is somehow that Z of G hat gamma comma 0 identifies with Z of H hat gamma comma 0. But in Kortewitz isomorphism, there are some co-invariants. And because of the co-invariance, things somehow work in the wrong direction. You can map from G to H, but not vice versa. But the thing is, at the level of Langlands parameters, once you twist, things are still well defined. The thing is that, so somehow what I'm doing is that at the level of Langlands parameters, the map omega of LH to omega of LG does exist. So though I cannot transfer unramified characters, the way the infinitesimal characters differ from unramified characters is via finite morphisms. And, suppose, so if you know that, something is regular, then after descending via finite morphisms also you get something regular. Now you know that the descended thing is well defined, and somehow only the descended thing is well defined. So yeah, sorry, I mean, it's yeah, so anyway, let me try to say it this way then. Z of H hat gamma comma 0 and Z of G hat gamma comma 0 can be identified. But I don't think Z of H hat, the inertia fixed, and Z of G hat IF can be identified. Kortewitz isomorphism needs to relate these two. The thing is, once you take the inertia fixed, then you have to take the Frobenius coinvariance. Yeah. Yes, but the stable Bernstein center should precisely be the ones which act by the same scalar on each L packet. That's the point. Yeah. Yes. But on the other hand, if you take SP4 and take a cuspidal unipotent and the unramified subquotient, which is a discrete series, then Bernstein center does not act by the same scalar on those two, but the stable Bernstein center does. Yeah. Yeah. No, but you see, if you look at Kaleta packet or something, if you look at a packet which consists of entirely supercuspidals, the Bernstein center acts by different scalars on all of them. Thanks. Hi. Yeah. So no, that's exactly the way in which Karzan, Warshawski, and Bezrukovnikov state the stable center conjecture. So it's not obvious, and it is a deep fact. So what you are saying is actually a very deep question, because it's true, but no one knows how to prove it. But actually the Lie algebra version of it is true. One knows how to prove it, and that is Walsh-Pershey's deep result that Fourier transform of a stable distribution is a stable distribution. Sorry. Yeah, so that was this remark that I mentioned in an earlier slide. Let me try to go to that slide. Yeah, so if you look at the last line on this slide, you can see for groups over R, infinitesimal character determines the discrete series packet. That's the same as saying that tempered packets are precisely the common eigenspace of stable Bernstein center. The stable center for the real groups is just the center of the enveloping algebra. Yeah, so that I don't know. Actually, that's a very interesting question. So I would like to see if there is something more than the center of the enveloping algebra, which can be called the Bernstein center for the real group. But you see, if you look at the center of the enveloping algebra, they act in the same way on every discrete series packet, right? So, those are actually the stable Bernstein center. Oh, okay. I did not know that Savin discovered this. Maybe, thank you. That was always something that I wondered about.
What did he discover? I'm not able to hear Dipendra.
Yeah. No.
Sorry?
What did he discover? I was so when the audience speaks, then we don't get.
Sorry, I'm not able to hear you fully. Could you?
Dipendra mentioned that Savin discovered something, but I don't know what was the comment.
So I'm hearing the first part of the sentence, but not the last part.
Okay. Hello.
Yeah. Thank you. So yeah, I would like to yeah. Yeah. Yeah, I was actually always wondering about it, and now thank you for answering this. Yeah. Hmm. Hmm. Yeah. Yeah.
Nothing specific. So Sandeep, like
I
what
can only
about,
barely hear you actually.
would,
If you can take the phone, then
to produce equivalent state questions for by descending depth? Hello.
hello.
Oh, are you able to hear me?
Yeah, I cannot hear from Zoom somehow. Yeah.
Like, could there be an approach of
Okay.
producing equivalent
Yeah.
questions for
Yeah.
by, you know,
Yeah.
by descending depth?
Yeah. So so I'm very sorry to everyone because I did not realize. I did not know what to do with the way Zoom was behaving with the other computers. So
Huh.
yeah.
Hello.
Thank you. Thank you.
Oh, okay, okay, that's fine. Okay, it's not important.
Yeah. Yeah. I'll send the slides too. Yeah. 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 Thank you very much. And yeah. Thanks. Yeah. Thank you. Thank you. Thank you.
So I thank the organizer for the opportunity to talk here. I'll speak, so let me just write the. This will be the title of my talk. So this is work done in my thesis, and so this is joint with my thesis advisor, Professor Arvind Nair. So I'll just so let me begin. So let me first recall the Leftist, the term Leftist properties for orthogonal groups, among which I will just give a quick introduction to each of the terms. So let me state this first theorem, which is the weak Leftist theorem or the Leftist hyperplane theorem. States that let X be smooth projective variety. So we are working over complex numbers. That is all this which is needed. And y contained in X. Hyperplane section. Then the inclusion y to X induces pullback map in cohomology. All the cohomologies will be with Q coefficients or C coefficients. So here maybe I should strictly write this. Yeah. This is the pullback map in cohomology, and the theorem says that this map, or rather I star, is isomorphism for and injective for, so injective will hold up until dimension y. So okay, this theorem is maybe one of the interesting things could be that we can understand this more maybe complicated varieties in terms of simple varieties. At least it's cohomology up till some degrees. Maybe just a quick. So of course I'm not going to prove the theorem as such, but I will just maybe give maybe one or two kinds of proof which are generally be available in the literature. So we have the following short exact sequence. Okay, so maybe give some notation first. So let U be the complement. So note that since Y was assumed to be already a hyperplane section, so U will be affine, and X was smooth, so U will be affine smooth. And then we have a short exact sequence, no, sorry, long exact sequence with these terms. Yeah, right. So I'm writing X, but stands for the complex points. This is just the general usual Betti cohomology. Yeah, and so on. now we can just supply here the fact that HICQ equals 0 for every I strictly less than dimension y. Right. So this not sorry, not y. It should be u here. So this which is same as dimension x, which is same as dimension y plus 1, since I've taken a hyperplane section. So this immediately tells us that right, I mean, since for I strictly less than dimension y, both the terms here and here will vanish, so it will be an isomorphism. But for for I dimension y, this term may be non-zero, so we will just have injectivity, but this will still vanish. So for I is equal to dimension. So this implies the theorem. So this is one kind of proof which we can give, but this proof will sort of, I mean, the kind of problem we will want to look at this proof, we will not be using this kind of argument. So another argument is maybe a little roundabout way of looking at things, which is we can also say that, I mean, hard left shades will imply weak left shades. I'm maybe not. For my purposes, I will only be interested in this statement, and we can just keep this here. So it is injective for I less than dimension, and this is the kind of statement which we want to generalize to locally symmetric space. Yeah, right. So X is projective, so it will have some ample line bundle. Say L, it is smooth, so I can look at this first Chern class or something, and then I can take cup product by these Chern classes. So I will have a map from cohomology of X to plus IX, not plus I. So maybe we can, let's try to make it symmetric. N minus I to N plus I, where N is the dimension of X and I bigger than 0. Then we have this cup product by I times, right? So this is something in second cohomology. So this map is an isomorphism. So this is all I will be using. Hardlow-Schutz says little more refined data about, I mean, you can write these cohomologies as primitive classes and all, but yeah, maybe those are finer questions and I will not need them. Yeah, so but to know something about this map, what we can do is, so I have.
Sorry, one that statement about cohomology of U0, that's also somewhat of a.
Yeah. So one argument is using Morse theory, which says that the cohomology of U is non-zero only until the dimension of U, but by duality we will get that the compact support. Another argument is given by, I think given by Madhav Noori in his paper on, but that is a completely algebraic argument, uses things like John Lully's trick to, but I can't recall that proof now. Sorry. So all I mean is, these are all algebraic varieties, and we are taking Betti cohomology. Yeah, this is singular cohomology, but by algebraic proof, so the Morse theory proof is completely topological in nature. We just say that this affine thing, they have only cellular structure up until dimension U. But in by algebraic proof, by taking some other variety, but with cohomology in some very bad constructible sheaf, that argument will be reduced to something about AN, affine plane, and then there one can do something. So here the sheaf is the constant sheaf, but we can make the sheaf worse, but make these varieties better, and then we will have more control over the variety, but lose some control on the sheaf. Then maybe something can be done from there to achieve this. Sorry, I don't recall that proof.
This is the proof given in
Oh no, this is the paper called Constructible Sheaves, where he proves that derived category of sheaves, constructible cohomology is same as derived category of constructible sheaves. There is like the paper in which he proves this as main. So basically in this paper he proves the characteristic zero analog of Bailinson result on perverse sheaves. Yeah, sorry, I forget the argument. It is a little involved, so yeah, I can't remember it. Sorry, yeah. It's yeah. So I upper star is a map from HIX to HIY. And there is the following map from HIY to HI plus 2x. So basically this comes from, I mean, we have this triple like this, or maybe, this is again some kind of a, yeah. We have a triple like this associated with this. There are two long exact sequences. One is what I have written here, and then there is another one of which one of the terms is this upper streak map, or maybe this is called the Julian map as well. And all we want to say here is that the composite, this composite is this is just cup product with the class of Y. Now using this, we will get that for I less than dimension Y, which is strictly less than dimension X, this cup product map is injective by hard Lefschetz, right? So is injective for when, so maybe I can put star in H I X. No, sorry. Yeah, right. Right. So this will imply that the composite map is injective. That is, this is injective on, so maybe on HIX for I strictly less than dimension X, which will certainly imply that I upper star is injective, because that is the first map we have. So this implies that I upper star is injective for I strictly less than dimension X, which is same as dimension, and which is the theorem. So, so basically this is the, I mean, this the second, some argument of this flavor will be used to prove weak Lefschetz properties for orthogonal, should be orthogonal varieties. Sorry. Locally symmetric space. No, these are orthogonal, so these are in, so I should say maybe rank 2, so they will be locally symmetric varieties. So there is a little difference up to connected components, but so maybe I can erase that and write locally symmetric varieties. I will be working with locally symmetric varieties. So, So maybe you can. And so after this quick introduction, maybe let me just go ahead and set up some notations which will be required. So maybe in the, it says maybe 0. So let V comma Q be a vector space equipped with a quadratic form of vector space over Q, and Q is a quadratic form, non-degenerate. Okay, non-degenerate. such that the signature of Q on V base change to R is 2 comma n. So basically, and let us, we can consider the orthogonal group of transformation of this space, since Q is a non-degenerate quartic form. So we can consider this, and the real points of this group is, so this is defined over Q again. So the real points of this group is what we know as SO2 comma n. Q, vector space over Q. So I mean, for the reason that I want the groups to be. Yeah, I mean, later we will want to talk about some arithmetic groups. So that reason, this is right, and W Q is to W be a subspace such that nature of Q to W is 2 comma n minus 1, and let us denote this by, so maybe I'll just skip Q restricted to W because it's clear, and this is again an algebraic group defined over Q whose real points is SO2 comma n minus 1. Now, I mean, just using the decomposition that directs some identity vector space with trivial quartic form. This immediately tells us that H is embedded inside G. So what to do is take an orthogonal transformation of W comma Q extended by identity on this. So basically it just takes an element H, maps it to in some matrix fashion H comma. So now we have two groups G and H, and yeah, so these are orthogonal groups. One is a subgroup of the other, and we can look at some, these locally symmetric spaces, or rather varieties associated with them, and ask some similar question if certain kind of Leftist properties, some version of weak Leftist can still be proven. But this is non-trivial basically because, I mean, of course, weak Leftist is available, and these are all will give us codimension 1 varieties, but they may not be hyperplane sections. So there is something to be said there. Right, so more setup. So let this be maximal compact, and this is just notation. Yeah, in some embedding it is. Yeah, they're generally not. Yeah, that is okay. Yeah. So this is again maximal compact. So we can choose K such that this intersection is again maximal compact, right? So what this will allow is for us to, so we can just denote this space by X, and this is XH, and we have such an inclusion just given by the inclusion of the group H in G, but rather the real points of the group H in G. And so this now X respectively XH carries So note that there is a left action of the real points of the group here. That is ISO2n. So carries a left GR invariant complex structure. And similarly, XH carries HR invariant. So basically this complex structure comes from the fact that the maximal compact subgroup of SO2n contains, at least it is one maximal compact subgroup. So K is of the form SO2 cross SOn minus, no, sorry, SOn. And then SO2 is in the center of this, so it will act on the tangent spaces here, and this act, so basically this is a circle, and the action of this is what gives the complex structure on GR mod K. That is okay, so maybe so these are called symmetric spaces, and we want to get to locally symmetric spaces. So we can consider quotient by some arithmetic subgroup. So let gamma contained in GQ be arithmetic subgroup of subgroup of G. Right. So so by this I mean G has, so we can consider any faithful representation which is defined over Q. This is a Q vector space, and in this Q vector space we can choose any lattice, and we can look at the elements of G in GQ such that G stabilizes this lattice. So these are all arithmetic subgroups, and we can show that all arithmetic subgroups are commensurable to each other. That is, their intersection of any two arithmetic subgroups have finite index in both of them. These will be some well-known properties of arithmetic subgroups. Anyway, so we can, in fact, we'll so let gamma be neat. So basically, this technical condition tells us that gamma is torsion free. It tells us even more that one can take some gamma intersection with some parabolic, project it to the levy of the parabolic. Whatever is the image will again be torsion free. So this neatness is some condition which ensures that all these things are also torsion free, so that we will not have any trouble, when dealing with compactifications, etc. But we do not really need this. So I just wanted to mention that. But for our purpose, this is good enough. We torsion free. So this implies that. And of course, gamma is contained in GQ, so let gamma with an arithmetic subgroup of GQ. So gamma will of course act on this space X by left translation. So we can consider this space gamma quotient X, and it's denoted by X gamma. So these are called locally symmetric spaces. Examples of locally symmetric spaces. Of course, and since the complex structure was GR equivariant, so what we will get that X gamma is, so of course gamma is torsion free and X was the manifold will imply that X gamma is a manifold. Now in fact we have something more, is a complex manifold. Yeah, but we still don't have any algebraicity properties, but there is a theorem, basically the theory of Bailey and Borel, in fact constructs compactification of this. first as a complex analytic variety, and then they say moreover it is algebraic. It is called minimal compactification. So this stands for minimal so it first constructs a x gamma star as a complex analytic variety, and then sort of tells us that using some Chow lemma kind of argument, embedding it in some projective space, tells us that this is algebraic. In fact, it says even more, this is quasi-projective. So, sorry, this is projective, so this will be quasi-projective. And since every, all our data is, right, so now we can take complex points of this, and this will be the sort of, this is the complex manifold x gamma. Okay, so maybe this doesn't. Here I mean x gamma as an algebraic variety. I just wanted to emphasize that the complex point is the complex manifold x gamma. So things are fine. So from here on onwards, I will not mention the complex points of x gamma to say that I mean I can confuse the two. Right. Okay. So now I can of course intersect it with HQ and call this gamma h, and I can form these. So gamma being torsion free will imply gamma h is also torsion free because gamma h is contained in gamma. So it again acts on xh, and we can form this space, which is to be denoted as this. Right. So we began with two groups G and H, SO2 comma n minus 1 contained in SO2n. We took the quotient by maximal compact subgroups on the right hand side, took the quotient by some nice discrete subgroups like arithmetic subgroups on the left hand side, and we have these locally symmetric spaces. And there is a, so H contained in G, this inclusion will give us a map like so. This map may not always be injective, but it is finite. So in fact, after assuming that gamma is small enough, we can always assume that this map is injective, need be. Maybe let just make sure that, so the dimension of x gamma is a complex manifold or as an algebraic variety is n, and n of x h gamma h is n minus 1. So it is a divisor, and right, I mean it is a divisor, and we can ask, so yeah, you probably will want to know if something like weak left shades is true, right? So there is this map I, and it gives us some like so, and we ask if this is injective in certain degrees, maybe for I is equal to 0, but degrees further than that it is not clear. In fact, so perhaps it will be good to rephrase the question, and so this gamma is, I mean we can vary gamma and look at the question as a uniform question. What I mean is we can rephrase it as following. So let us just define this script x, hi of script x. So this is just some notation. Yeah. So given arithmetic subgroup gamma, and so this is the partial relation, gamma prime is contained in gamma, then we say that gamma, I will have a map from, yeah. So this will give me a map from x gamma prime to x gamma. This will be a cover. This will give me a map in cohomology. So we can form this direct limit. This partial, yeah, we can put this partial order on it. Gamma, if gamma prime is contained in gamma, then we say gamma is bigger than gamma. Sorry, gamma prime is bigger than gamma. Yeah. Right. So this direct limit makes sense. And now all these bunch of maps will similarly induce for me a map to HIXH. So whenever I write H in the bottom, it just means the same object defined in a similar, almost the same manner by replacing G with the group H. So now we can ask if this map is injective or does it have certain nice properties. I mean, the reason being that, okay, oh my, okay, I think is it broken? Yeah, so as I was saying, answering, I mean, if this were to be injective, we can look at, I mean, all these HIX gamma are contained in here. So that map will be injective. So what I mean is answering this question will answer our question for all gammas. So now we can try to understand this map. So we can call it the little restriction map by little res. And we can ask if this map is injective in certain degrees. Maybe, considering that we looked at weak Lefschetz theorem, so maybe the expected bounds will be somewhere around for I less than dimension of this xh gamma h, or recall that the dimension of these were n minus 1. So for the group SO2 n minus 1, the dimension of this is n minus 1. So we can ask if this is injective. Yeah, so these are all covering transformations. These are all torsion covering transformations. Yeah, in fact, right, so gamma, I mean, if gamma prime were normal in gamma, which we can assume by going to a smaller subgroup, then this will be, I mean, x, so this will be a gamma quotient gamma prime Galois cover, and we can just take, it will act on the cohomology. You can take gamma in this invariance of this thing, and it will give us this cohomology. Yeah. Huh. Yeah. So we can ask if yeah, this map is injective, but that is also not true. Yeah, so this can be seen by comparing the the growth of cohomology as gamma becomes smaller and smaller. So we can see that these restriction map will never be injective. So the question as negative answer. So the argument was like compare growth of cohomology as gamma. I'm writing gamma tends to 0. I mean gamma becomes smaller and smaller. Huh. Yeah. Right. So that is. Yeah, but I mean for all I less than this. So at least like the first. Okay.
So I'm not clear about why, because of the group conditions.
So for example, for
Let's say for n minus 1.
yeah. Right. So for n minus 1, I don't know, but maybe for when I is equal to 1, let's just say, and x is some locally I mean, here X gamma is some locally symmetric associated to something, say some very large group, say SO maybe 2n or yeah, n. No, the H1. Right. Yeah. Yeah, H2 is the smallest one. Yeah. There, I think we want to say that the no. So yeah, that is true. But so
No, I just meant to say that below the middle degree, the growth is anyway very limited, and therefore I don't see how the asymptotics force you to have non-negative.
So I think the argument is probably somehow maybe this can be bounded by some by some constant and then some volume by above, and this we have to get some lower bound of here.
These are these conjectures of Sarnak.
I don't think it uses all that. Maybe
But just to know the asymptotics,
Mhm.
there is some asymptotics below them.
yeah, I don't know that. You mean in a sense how many times a discrete series appears?
Again, Gordon Savin's work, which says that it grows in a uniform way because it is contributed by discrete. But lower than middle degree, it is contributed by discrete. The growth is much smaller.
Okay, so maybe all I wanted to say is if we take in SO2n, and so my setup was maybe here it is a little difficult to compare, but for example, if I take this n to be like much larger than this n here, and then maybe some arguments can be like, for example, on second cohomology, by taking this n to be much larger, this will, I mean, yeah, I think there's some argument like this. At least I've seen this for in the SU1n case, but definitely this is rank 2 case, so maybe the same argument won't work as you pointed. Okay, maybe I should check again. Thanks. So 22 more minutes. Yeah. So now for G in GQ, can consider this left multiplication map. And here, this will induce for me a map from G gamma G inverse. This is again arithmetic subgroup. And this will induce a map in cohomology. So using this, what we can get is action of GQ on HIX. So recall that HIX for the direct limit of HIX gamma. So GQ acts, so we can club all this together and put action of GQ on this. So basically these are, I think, Hecka transformations. These can be, so, I mean, I realize that it should be maybe GAF, but GQ is good enough for our purposes. And now what we can do is we can consider this big restriction map from and the gth component, so the gth projection this is given by any class going to G dot alpha. Some complicated map, I don't know. And yeah, I mean, it in fact factors through some smaller subset of this, which is convenient for, you know, purposes of the proof, but probably I won't be writing much of the proofs today. So maybe it's okay to just leave it as it is. And right. One more thing. So just like HIX has an action of GQ, HIXH will have an action of HQ, and this small RES map is HQ equivariant. So basically we would just want to sometimes use like Frobenius reciprocity and make it GQ equivalent. This is contained in here, and this is so this is somehow the target which is convenient for the purpose of the proof, but maybe it's not really necessary here. Okay. Right. So once we have this map res, we can construct several variants of this map, and one can talk about res star, which is so HIX star. I can just define it here. Direct limit over gamma HI of X gamma star. So X gamma star, as recall, was the minimal compactification. It contains X gamma as an open smooth subvariety, and the complement of X gamma is of dimension less than or equal to 1. So basically we just add some modular curves and certain points. So that is X gamma, that is how it is meant. But of course that doesn't really define the structure. It is, yeah. So we there is this map we can define res star, and maybe some other map. Probably so now the fact that these are algebraic varieties are used, they will be used of course later in the proof as well, but the first application we see has that this has some weight filtration. So weight filtration and certain increasing filtration. Basically these carry some mixed Hodge structure, whatever they mean. I mean, Deline had defined it in his paper on Hodge theory, but we will not need many of its properties except for the fact that this has weight filtration. This is an increasing filtration. So let me just increasing filtration, which is I mean, yeah, maybe in natural in quotes. I mean, it commutes with pullbacks, push forwards, and other all these long X sequences, etc. We write the weight filtration will commute with everything. I mean, it will be preserved by more or less all these 6 functor that we can write. So these J lower star, lower shriek, I upper star, upper shriek, these things. Anyway, so using this, we can say that basically the map res star. So using this, we will define a filtration and call it Wj. This is defined to be the limit over Wj Hix gamma, limit over gamma, and So once we have certain filtration, we can take its quotient. Let's we'll denote it by standard notation GRWJ, and the map res, since it is induced by all these small restriction map, because of these small restriction map were in turn induced by something which are all algebraic, so they preserve the weight structure, this weight filtration, and so it will induce a map on all of these weight filtrations. So basically, it induces maps from here and then it will induce a map on graded quotient. This map is of some interest to us, but we are only interested in the top. So now J was any subscript here, but now we are only interested in top. The reason being that these have certain better properties, so which we'll just see in a moment. Okay, so we have these maps res and gr res star. Now, and okay, there is another thing. Yeah, there should be a product here. G in GQ product. G in GQ HI XH. And what are these lower shrieks? So just again a notation. HI lower shriek of any topological space is just image of compactly supported cohomology in the usual cohomology. So there is a forget supports map, and we are just taking image of the compact support cohomology in the usual cohomology. So yeah, we have these three maps. I mean, okay, the only reason to introduce all these auxiliary maps about GRS star and lower shriek is that one is not able to prove the theorem directly here. Okay, so what is the theorem? That is the question. So we want to prove that the map res is injective. So this map will be injective is the is what we want to prove, and these are somehow the geometric I mean the content of those restriction maps. So basically the arguments to prove this will be mostly geometric except for a little analytical input, and when we come to the proof for this, we will need some representation theory. Right, okay, so maybe I can erase this part of the board. Yeah, but yeah, only ith one, because okay, so what I will want to do is this so HIX over HIX star will have a map to the intersection cohomology of X star, X gamma star, and then this will map. I mean, this is the image basically. Okay, so maybe I can just outline the.
The weight filtration is so nice that the other pieces are.
Yeah, these. Yeah, but this is the general fact which one can.
So the only order piece is the item.
Yeah, so if we consider this map, so, or maybe for any proper variety. Sorry, I'm writing it correct. Yeah, this is fine. So basically, there is a map like this in general, right? And these are all proper, so this is okay. And all I want to say here is, yeah, this is injective. I mean, this is of pure weight I. So definitely it will factor through this. But now I want to say this is moreover injective. So one can use kind of, yeah, maybe.
No, I'm sure there is something going on. Yeah, why should it be concentrated in the highest weight filtration?
Yeah, because this is pure weight. this has weight less than or equal to I. So it will definitely factor through this. To prove injectivity, we require something. So basically what is required is that, I mean, I'm not very comfortable with this language, but okay, QX, one can work in the language of maybe pixel modules or maybe use decomposition theorem. So there are two ways to go about it. So there is one fact which is, Deline tells us that if we take resolution of singularities of this thing, then this will in fact be like this. This is in like Hut 3 by Deline. And now using this plus the fact that, I mean, there is such a decomposition, right? We can write. This is exactly a decomposition theorem. That we will have an inclusion like this. And since the map factors through here, I don't know if I'm making sense. X and X, these are resolution of similarities. This is not.
X and X bar could be very different, or maybe just minor difference.
Yeah.
And to say that it is concentrated in I means that somehow X and X bar are essentially the same.
No, all I mean is this is an inclusion, that is all. And this is not an isomorphism. So the map will definitely factor through this because of, so this has weight less than or equal to I. This has.
Why ignore other weights of it?
Oh, yeah. I mean, those we cannot handle actually. That is the first thing. I mean, one would, that is the first thing.
Why not other graded pieces?
Yeah, definitely they are interesting, but do not know how to really prove. And yeah. I mean, okay, one would want to prove, of course, like restriction map. I mean, expectation should be that on all of this cohomology, but one is unable to really prove that. I mean, that should be the case because in co-compact setting, when all these things are compact and there is no need to compactify, these maps have been proven to be injective by earlier works of Venkatramana, Bergeron, and so one would expect this to be true for all graded pieces, but unable to prove this. So basically, this piece is what. Is what can be captured by geometry. And the other fact is, since this is embedded inside intersection cohomology, and recall that in the beginning we said that our proof will follow, the argument along the lines that hard left shades implies weak left shade. So then we can, we do have hard left shade on intersection cohomology. So now that is the geometric content of the argument. Okay. Okay, so maybe let me think. Yeah, I can do that. So maybe I can slide certain short exact sequences and just to keep the notation here. Sorry, there is a lot of notation. Probably there should be maybe. So maybe you can just write down. So note that this map is yes. Yeah. So the first theorem this is injective for. So this is injective in optimal degrees, like whatever we will extract. And then as we try to move towards, so basically we will write certain short exact sequences which will tell us that the cohomology here can be understood as the cohomology here plus certain contributions coming from the boundary. So basically removing the boundary will allow more cohomology classes. So yeah, the second is so there will be certain loss in degrees. In the middle degree, don't know how to as of yet answer it. Okay, so about the So we can call this theorem open, and this is like top weight, just some name to maybe remember. So to prove the theorem on open this variety, by open I mean the X gamma, because they are not compact. So X gamma star minus X gamma, and this is open, dense, and this is closed. Right, and now we can write certain long exact sequences again. Should be HIC X gamma to gamma star to some, sorry, to write as some sheaf here. So let's just write J and I. The constellation. Anyway, so no, all I mean here is we can apply, all of these have weight filtration that is coming from some theory, and we can apply this, we can take this top weight grade piece everywhere. Right? Sorry, I think I've written something wrong. Yeah, we can take this top weight grade pieces everywhere, and now we want to prove, say, something about this. Okay, now we can ask, okay, why is in the degrees we are interested in, why is this the same thing as the cohomology of X gamma? That comes from the fact that in fact this is isomorphic to intersection cohomology in certain degrees, like below this. The reason being that strata are not of dimension bigger than 1. So they are of dimension less than or equal to 1. So by strata, I mean we are only adding, so the boundary is, by boundary I mean this set is of dimension less than or equal to 1, which somehow tells us that this is not pure in all degrees, but in certain degrees, lower degrees, this is pure, and so this will somehow tells us all the picture. So we can apply the graded, this GRWI here. This is exactly HI lower sheet, which suppose we know. So now our aim is to understand this. To understand this, this has two kinds of boundary components, some one dimensional union, some zero dimensional. So that means we want to understand this sheaf when restricted to each of these. Restricted to one dimensional. And so understanding the hypercohomology, or rather the sheaf, comes down to understanding some Lie algebra cohomology. So maybe that is not, I mean that is the easier part here. And understanding the restriction to this is again cohomology, but this is something complicated, and we see that. So let me just write this. Maybe, yeah. If we want to understand the HI cohomology. Okay, so this is not entirely correct, but yeah, maybe we can just go ahead with this. So here is locally symmetric space associated to. Yeah, sorry, I'll just take 2 more minutes and simply write gamma SO 1 comma L minus 1 KL. So L has certain meaning. Gamma L will mean that this arithmetic subgroup. Okay, before that I should mention that these zero dimensional strata arise from some parabolic subgroups, parabolic subgroup P, which is the stabilizer of the flag 0 contained in line. So this is the isotropic line which is contained in the perf and which is V. So when we write the Levy decomposition, this will come out to be SO1 n minus 1 and the Levy will be GA power n. Yeah, sorry, this is the Levy, this is the this is the Levy decomposition. And so the Lie algebra cohomology that so basically we want to understand what this hypercohomology looks like. This can be understood as so we want to write I here. So I by 2 whenever it makes, if I is even, okay. So and wedge I by 2 Lie algebra of GAN. Right, dual. Right, so note that SO1 comma n has an action here. This will tell us that right. I mean, so this will become a local system on this space. Sorry, I'm unable to explain well. So, okay, to prove the theorem here, we want to understand something here and something here. So we will also know from some weight arguments that this is injective. So suppose we know the theorem here and suppose we know the theorem here, then we will know that there will be a similar short exact sequence for XH. So we will know that if we can prove injectivity here and injectivity there, we will know the injectivity on this variety we are interested in. And now the question is to understand the injectivity here. So there will be something similar for the H as well. So all that it boils down to understanding how the restriction maps behave for these orthogonal groups of rank 1. Right? So because the ith cohomology can be understood as the I by 2th cohomology, where I is 2k. I by 2th cohomology of some locally symmetric space assured SO1 comma n minus 1 and some local system which is in there. And okay, so finally, this is the representation theoretic part of the argument, which saying anything about. So now one has to use the results of Bergeron Clausel. So they had proved injectivity of res for the groups SO1 comma n minus 1, but they assume co-compactness. Yeah. Plus, I mean, in their case, local system is trivial, but that is not too big of a hurdle. So this is not very important. Maybe I should not underline it. So they assume co-compactness. We do not assume co-compactness here, and we want to prove that these restriction map so wedge, it's the same index I here. So maybe we should write K to so this will be on n minus 2, right? And yeah, this is injective. I mean, we will also have to take some similar products. Sorry, yeah, it is. I'm way out of time. So somehow we want to prove this. Proving this, again, we will write these short exact sequences. There will be again some HI lower streak kind of thing, and again some boundary. In this case, the boundary is easy. Understanding HI lower streak is the main part. HI lower streak can be understood as cuspidal cohomology, and that is somehow the main thing. So HI lower streak equals cusp in rank 1 plus again it's an application of Burger-Sarnak argument. It is the Burger-Sarnak argument plus isolation hypothesis. This is made by Bergeron and proved by Bergeron and Clausel in 2013, I think. Yeah. Sorry, it is neither here nor there. Thank you. I'll stop here. Yeah, I mean, we have similar theorem for SU1n as well. These are, but yeah, I do not. I mean, so one thing is. So some geometric. Yeah, but yeah, I mean, there is geometry in understanding this part. Yeah, algebraic. But P2J is. But if the rank increases, these arguments fail miserably. So some other techniques will probably have to be used. Because if the rank is more, this compactification is pretty bad. Then, huh? Yeah, it is for locally symmetric, Shimura varieties, but it depends on the rank. So, like as I said, one dimension, zero dimension comes from the fact that when we take the parabolics defined over Q, they are very simple to describe. They are either a stabilizer of this, and its levy will look like this, and other. So because you see this one dimensional coming in, because the parabolic is the stabilizer of this flag, which is the two-dimensional isotropic subspace, and so in the levy there is a GL2 here. But you can have like higher rank groups, and then the compactification will also be worse. So one probably will have to employ certain other methods. I mean, SP2J is certain. Yeah, I mean, definitely you can decompose this as, I mean, not this, but rather the cross plus Eisenstein. But we are proving the result on all of this thing. So, sorry, I did not understand the question. Yeah, so it is. Right. Huh. There's the Eisenstein. Yeah, I don't know. Yeah, I have no idea. Okay, but probably since the target is something infinite dimensional, I mean, you have to take translates by many of these group elements in GQ, maybe to understand Einstein convergence in terms of smaller groups is not, because restriction up to probably these finitely many components will not work. One has to include like entire product G over GQ. That is what I knew. So yeah, I don't know. Maybe. yeah, definitely that is something to think about. I don't know, but definitely, for example, Bergeron, he used some representation theoretic techniques. So, for example, just note here that which is like the surprising part, and which is the reason why one has to resort to representation theoretic methods, is that this locally symmetric space is far from, like, is not algebraic. So there is no way to understand the interior cohomology in some other sense, or some part of the cohomology in other in some geometric manner, right? So since he had used some representation theoretic methods, he is able to prove something on homologies. But yeah, I do not follow. Yeah, but definitely the question makes sense. You can ask on pi one. I don't know how to. Oh yeah, sorry.
Recording stopped. Recording in progress.
Hello, am I audible?
Yeah, you're available. Yeah, Prashant, you can start.
Okay, thank you. So I'm sorry that I could not make it offline. I'm not well, so it will be happening online. So I will start. So the title is Harishchandra induction and Jordan decomposition of characters. It is based on our current project with Professor Manish Mishra. This is joint work with Manish Mishra. And so Lustig defined this uh, uh, for a connected reductive group. So if you take its FQ point, so finite connected reductive group, Lustig defined the notion of this Jordan decomposition. Basically, it gives you parameterization of these universal representations of G in terms of unipotent representations of some smaller groups. And so it's a natural question, how this parameterization is behaved with respect to Harishchandra induction. So this problem is this is studied by for classical groups or classical groups with connected center. Uh, the Fogg and Srinivasan proved that uh, and Srinivasan showed that these parameter, this Jordan decomposition commutes with Lustig induction. And so, and for simple groups with connected center, this was studied by Geken. So this was in this book of Geken Male, this recent book. But they obtained this by case manner. And we resolve this commutation problem for all groups. So we have proved this following theorem. There exists a Jordan decomposition which commutes with Harishchandra induction. Chandra induction. So we'll prove this theorem at the end of this talk. So let me fix some notation. So G will denote a connected reductive group. It's connected reductive group over a finite field FQ. F is G to G a Frobenius morphism, corresponding Frobenius morphism. And if you fix a maximal torus containing some Borel, so these are the F stable maximal torus and Borel subgroup. Then one can define the dual group. So this is G star. This is again a connected reductive group. So this defined using this root datum. So it is correspond to the dual root datum. The dual group. This again defined over FQ, and let's denote it's the corresponding Frobenius morphism by F star, the Frobenius. And so for this maximal torus, there exists a corresponding maximal torus T star, which are in duality, and this Borel subgroup. These are F star stable. Maximal torus and Borel. Then, so we have this isomorphism between while group. This isomorphic to the corresponding while group. So let us denote this isomorphism by delta, and it also gives you isomorphism at the level of FQ points. So if you consider a pair of a maximal torus and its character, so theta is from TF to QL bar. So this L is different prime from P. Lustig defined this virtual representation corresponding to each pair T comma theta. Lustig, Delling and Lustig constructed this virtual representation. And using these virtual representations, Lustig classified these are set of all irreducible representations of GF in terms of this Lustig series. So for that, so this is a fact. If you consider this pair T comma theta up to GF conjugacy, then they are in bijection with pair of these maximal tori in the G star, which containing a fixed semi-simple element modulo the G star F conjugacy. So S belongs to G star F. So then we will just denote this by this notation RT G of S. Just this virtual representation. If T star comma S correspond to the pair T comma theta. So this is just another notation. And using this, we'll just define Lustig series. It's called as a rationalistic series. So this is defined as, so this, you consider all those irreducible representations of G of F such that this inner product comma rho, this is non-zero for some F star stable torus T star such that S belong to this. So And if it denoted by unipotent character, they consider those Lustig series which correspond to the identity element. So this G comma 1. So these are the unipotent representations. And this is a fact key. These the Lustig series form a partition of set of universal representation. Yes, where this take up to semi-simple conjugacy classes. Simple conjugacy class. G star. Okay. So we have some partition of universal representations of G, and so as I say, Lustig introduced this notion of Jordan decomposition of characters. This gives us a parameterization of each of these series in terms of unipotent representations of some other group. So let me just recall. This is a theorem to Lustig. So this is firstly true for the group with connected center. So assume that Z of G is connected and let S belong be a semi-simple element. So let us denote by H the centralizer of S in G star. So note that, so we have assumed center is connected, of Z of G is connected. So this H is also connected, and there is a bijection from these two, these unipotent characters of HF star. So let us denote this bijection by JS. Then it satisfies some natural properties such that for any F star stable maximal torus T star contained inside H, we have R T star G, so comma rho is equal to epsilon G times. So these are the epsilon G and epsilon H are some signs associated to G and H is equal to R T star H, comma. So here I am taking the trivial character and JS rho. So Lustig first proved it for these connected center, then it extended, and again later he extended it to for disconnected center, and for disconnected center it's not a bijection, it's a surjection. So with G is any connected reductive group. So no assumption on center. Then there exists a, you prove this, there exists a surjective map. Again denote by the same notation. This is from this Lustig series 2. So unipotent character of this connected component of EH. So in general, this centralizer need not be connected. So, and these virtual representations are initially defined only for connected groups. So you consider this unipotent characters of S naught and modulo the action of HF mod H naught F. So H naught is normal, so H act on H naught, and we consider those orbits under this action. So we prove there is this surjective map, and it satisfies the following property, such that if rho is in some orbit O and E star is a maximal storage of G star containing S, it belongs to. Then this inner product comma rho is equal to this up to sign summation over those. We take all elements in this orbit and you consider a rho prime. So this is in S naught and this is in G. So if G has connected center, then it gives you this previous result. So and by Jordan decomposition means a bijection from, so this bijection from Lustig series to unipotent character such that it satisfies this pairing condition. So to prove there exists a Harishchandra induction which commute with this Jordan decomposition. So the key result to prove this is the compare the endomorphism algebras of the Harishchandra induced modules. So let me just state. So let's also introduce some notation. Let A will denote it will be a split Levy subgroup of G. So L is H stable. And let us denote by A the maximal split torus inside the center of L. This torus to center of L. Basically a split part of the center, connected center. And so WG just the while group. Modulo L. And this L is nothing but the centralizer of this A inside G. So for a cuspidal representation, for a tau in it is cuspidal, let us define this subgroup of this while group of A. So W tau to consider all those elements such that this chi tau. So this normalizer of A naturally acts on L, and so this WGA, if we are considering F points only, so it also acts on LF, and so we get action of this while group on universal representations of this finite group LF, and we consider those representing for a cuspidal representation, we consider a stabilizer under this action. So let's, so that is W tau, and so this next result is due to Wortleller and also by Lustig and Gag. So this theorem says that G is connected reductive, or F. L is a F-stable split. Levi subgroup of G, and tau is a irreducible spatial representation of this Levi. Then this endomorphism algebra, this Harichandra induced of tau, so just opposite algebra, is isomorphic to the this group algebra of the while group W tau. So Howard and Lehrer proved that this isomorphism is up to some 2 co-cycle, and Lustig has shown that this 2 co-cycle is trivial for a connected center case, and Gack resolve the general case. Okay. So we are trying to prove that the endomorphism algebras are preserved under this Jordan decomposition. So to prove this theorem, that the result that endomorphism algebras are preserved under Jordan decomposition, it is enough to show that the corresponding while groups, that is W tau and W j tau, are isomorphic. Right. Okay. So are there any questions? Okay. So let's go ahead. So we are going to prove this proposition. Okay. Z of J is connected, and J is, this is a Jordan decomposition from to unipotent character. So HL is the centralizer in L star. So for every Levy, we can choose a Levy subgroup of G star up to G star F conjugacy. And so, okay, I forgot to mention. So these Lustig results only says that there exists a bijection from this Lustig series to unipotent character, which preserves certain property. But it cannot say how many bijections are there, or does there exist a unique bijection. So this Dean and Michel proved that there exists a, okay, maybe I will just state that result first. So this is theorem due to Dean and Michel. So assume center of G is connected, then there exists a unique Jordan decomposition of character which satisfies certain properties. Certain properties. And so let's take JS is the unique bijection from this Lustig series to this unipotent character, and then tau is a considered, then we will show that this W tau is isomorphic to WJS tau. So, and this implies this endomorphism algebra into G of tau is isomorphic to the corresponding endomorphism of algebra of unipotent. H of J tau. So this follows from this Ford-Lewis result. So for that, we will use this uniqueness theorem. So for this, consider so note for that, consider this lemma. Assume center is connected and let W belongs to this while group in element, and so this W star belongs to the corresponding while group element, so such that this W maps to W star under the delta. Then the following diagram comes. So so if you apply this W to L, so it gives the automorphism of L, but it need not say that about where the corresponding S goes. So it gives a map bijection from LF to this sigma W star of S. So it is just by composition with sigma W. So it is W star. So just compose with W inverse. And we have this unique Jordan decomposition. JS and unipotent character W star. So again, this is C. Okay, so I will just write L to say this is Jordan decomposition corresponding to the Levy subgroup L. So to prove this lemma, so we consider, so note that these two, this is a bijection, this also a bijection. So just take a map from go here, here, and here. So this defines a new bijection from this Lustig series to this corresponding unipotent series, and we will show that it satisfies the all 7 properties that are in the that assert this Jordan decomposition is unique. Okay, let me try. So let's define this new map. It's JSL. This is from unipotent character. So this is defined as, so rho is equal to this W inverse composite is W star inverse. Okay. And one can easily show that this JS satisfies the 15 and Fisher's result. So uniqueness theorem. So this means this by uniqueness, this has to be the original Jordan decomposition, and that means this diagram commutes. Okay. So and okay. So let me mention this. So to prove this theorem, we just use this uniqueness criteria, and after uploading our preprint, Lustig pointed out this result for connected center can be getting by looking at the proof of one of the theorems in his book book on the characters of finite group on characters of reductive group or finite field. So basically, this result can in connected center can be deduced from the proof of one of these Lustig's theorem. Okay, but we okay, and so this Lustig's proof is based on the parameterization and of while group and all of these things, but we only using this uniqueness criteria. Okay, so any question about this? So okay, so this is for connected center. We get the isomorphism between endomorphism algebra, and we also have so you know, so this is for one can get for arbitrary group. So yeah, this connected reductive or FQ. So no assumption on center, and this JS from to this is a surjection. Just from unipotent character of modulo the action of this group. This is surjection. Then this endomorphism algebra. So the ELA is again a split Levy, or this unit Harichandra induction. This is isomorphic to the page. So JS. So note that here we are considering uh, the morphisms which fixes the orbit. Yeah. No, sorry, not this. Okay, sorry, not exactly the same. But firstly, we have shown that this W tau is isomorphic to WJS tau. So WJS tau is defined as WJS tau is defined as so we consider those elements in the while group So this is WHA star such that those which are fixes this orbit. So, so that this W star acting on this orbit, same as this L. Yeah. So and then okay. So okay, we have shown this isomorphism between these two while groups, and as a corollary to this, one can say that if this, you can take two cuspidal representations tau and tau prime in the same series, cuspidal, such that is equal to yes tau prime, then one can get that these endomorphism algebras, the corresponding Harishchandra induced modules to G of tau is isomorphic to the this into G of tau prime. So that means if two elements correspond to the same orbit, then they have same irreducibility structure. The Harishchandra induced module have same irreducibility structure. And we also proved the structure of this the endomorphism algebra in terms of disconnected group, but it's somehow twisted. Okay, let me just write the result. So one can show that this if you choose a, suppose u tau is in some orbit, Js it's in this orbit, we take any particular element, then one can show that this series, again we can define this while group associated to this unipotent representation W tau and W tau modular U tau. So this is a split exact sequence. Split exact sequence, and using this and the Hort-Leller's result, one can see that the structure of endomorphism algebra is isomorphic to so the endomorphism algebra. So we are taking connected component here, HL naught to H naught of U tau, and this is somehow twisted. Okay, let me explain what this. So here denote this group by gamma. So basically here the endomorphism structure coming from this semi-direct product. So from this exact sequence, we get this W tau is isomorphic to W U tau, semi-direct product, this gamma. And the endomorphism structure on right hand side is coming from the sorry, here the tensor structure is coming from this semi-direct product in the group algebra. Okay. So using this result, okay, this one can define a bijection from. So okay, let me just say what did okay what we have. We have this W tau is isomorphic to W u tau, and this means irreducible representations of W tau are in. So this say are in bijection with irreducible representations of W u tau. Okay, but by the Hort-Lennard result, we have this set is in bijection with this Harishchandra series. So irreducible representations of GF. So these are the just constituent of the this RL G tau. So these are the constituent. So these are in bijection with irreducible representation of Weil group. And similarly, we have here. So for connected center, we have this. These are in bijection with irreducible representation of EH. Okay. If we know if Lustig series can, suppose we can decompose the Lustig series in terms of Harishchandra series. Sorry, Harishchandra series. Then one can get a map from Lustig series to the unipotent representation, corresponding unipotent representation. And this is a fact. I will just recall. So again, G is connected reductive and L is split Levy. Okay. Then this Lustig series is a disjoint union of Harishchandra series tau, where these are pairs are taken up to GF conjugation, and this tau belongs to the corresponding the Lustig series corresponding to S for real. Okay, so similarly we have this partition of this unipotent series, joint union comma E tau, and irreducible representation of okay. So as here we can see we have a, so this is a bijection from this Harishchandra series to the corresponding Harishchandra series. So we get a bijection from this Lustig series to the corresponding unipotent series. And okay, so now that means if we fix a, okay, here u tau is nothing but the image under the Jordan decomposition of tau. So if we fix a Jordan decomposition, decomposition for all cuspidal representations of all Levy subgroups, all split Levy subgroups, okay, including G itself. So such that this W tau is isomorphic to W u tau. So u tau denotes the image under Jordan decomposition of tau. Let's fix one such a Jordan decomposition for cuspidal, and by previous result we know such a Jordan decomposition exists, then we have this following result. G is connected reductive and center of G is connected, and let so then so for tau n cuspidor, and so this U tau will be the image under the chosen Jordan decomposition. Very important. Under chosen the decomposition. Then we have this map. It is so this is from representations from this Harichandra series. Tau to star comma U tau. So this is a bijection, and so we have a bijection for each Harichandra series, and by combining all these, we get a bijection. So you get a bijection from IS to unipotent character. So bijection such that this rho is equal to this up to sign 1 comma this j star. So this means, okay, if we fix a Jordan decomposition for cuspidal, then we can get a Jordan decomposition for all of G. Okay, so which satisfies, and so this is the main result. So this Jordan decomposition commutes with the Harichandra induction. So the above Jordan decomposition. Jordan decomposition. Commute with Harichandra induction. So that means if you consider this following diagram, so unipotent character. To so unipotent characters of so this is the Jordan decomposition for G. So this is just a above defined map for M. This is the from M to G. Okay. And here, so this is L is contained inside this L star is contained inside M star is contained inside G star, such that its S is in L star These are the split Levi subgroups of G star, and L and M are the corresponding Levi subgroups of G. Okay. So to prove this theorem, this is based on the again Hort-Leyer's comparison theorem. Let me recall what I just said, that this comparison theorem. So this follows from Leyer's comparison theorem. So it says that Lf comma tau be a cuspidal pair, and so note that for a we have this denote by I L tau comma M. So this is a bijection between Harishchandra series and the universal representations of endomorphism algebra, or the corresponding while group. Comma tau. Universal representations of W tau, but here we are considering inside M. Okay, where M runs over all Levi subgroup which contains L. Okay, then this bijection can be chosen such that the following diagram commits. That is the map between the comma tau to representations of this is while of tau correspond in G, and here we have map from so here is Harishchandra induction from M to G, and so this is while loop of tau inside M, and here usual induction. Okay, so this W tau M is contained inside W tau G, and so here usual induction, and L tau M. So then this theorem follows from here, because this bijection, the Jordan decomposition here, yeah, here. So this is defined by just comparing this set with this universal representation here, again comparing it with unipotent representation. So by again applying the comparison theorem to the other side, we get the commutation of this Jordan decomposition with Harishchandra induction. And similarly, we can define so extend this then we can extend this Jordan decomposition to case where z of G is not connected. So this is basically defined. So the Jordan decomposition in the case of disconnected center is defined using the regular embedding. So that is, you have this G2 G tilde is a regular embedding. So such that this G tilde, the center of G tilde is connected. And Jordan decomposition for G is defined in using the Jordan decomposition for the G tilde. And if you take a Jordan decomposition for G tilde, the previously defined here, then using this Jordan decomposition, one can define a this surjection. So using Jordan decomposition for G tilde. Using Jordan constructed above. Create a Jordan decomposition for G which commutes with Harishchandra induction. Harishchandra induction. So this recipe for constructing the Jordan decomposition in disconnected center is given by Lustig, and we just apply the same process. Then we get a Jordan decomposition for this G which commute with Harishchandra induction. Yeah, I will stop here. This was the last result. So this was the open problem as mentioned in this Gack and Malay's recent book. Does there exist a Jordan decomposition which commute with Harishchandra induction for all connected reductive group? So main ingredient of this is just the isomorphism between endomorphism algebras of the Harishchandra induced. Yeah.
Yeah, you can ask.
Hello.
Comments from Prashant.
Sorry.
Hello.
That might be
Yeah, now.
Hi Prasanda, you can hear us? Hi Prasant, can you hear us?
Sorry. Yeah.
You can
Hi.
hear us, no?
Yeah.
Okay. So I was just asking the audience if there are questions or comments. Okay, maybe a quick question. So this particular Jordan decomposition which commutes with the Harishchandra induction, you also say that it is unique or there could be several?
Yeah. That we don't know, but we know there existed this one thing. Yeah, because if we start with a cuspidal, we fix a Jordan decomposition for a cuspidal case, such that the corresponding while groups are isomorphic, then we get a one which commute with Harishchandra induction. But to check it is unique, we have to check that it satisfies these 7 properties.
The Din-Michel properties.
Yeah.
I think Manish has a comment.
Yeah.
One which commutes with the Harishchandra. Yeah.
Thank you. So okay, then I'll stop sharing.